We'll start with something that allows us to see the logic of the t-test. On page 395 of the field textbook, there's a side quest to run t-tests from only some provided means, standard deviations, and sample sizes. The context for these values is this paper. Board and Fritzen were following up on the successful psychopaths literature, and we're interested in the similarity of profiles between senior business managers and those deemed legal psychopaths by the state. The paper's argument is a bit awkward. The conclusion driven home is one of similarity of legal psychopaths in Broadmoor Psychiatric Hospital to senior business managers. Yet the analyses provide no reasonable comparison for the similarities observed. The CEOs only differ from Broadmoor psychopaths by X amount. Well, okay, but how much is a normal amount to differ from Broadmoor psychopaths? Compared to what? Non-senior business people or other normies may have sufficed for a comparison if the argument was for some sort of special similarity, but no such comparison was made. Whether the claim ended up being that the similarities were noticeable or that there were differences that were notable, they still need to lead with their sample in either case. The last line of the abstract argues that this similarity means personality disorders are not categorical. Yet if successful psychopath literature that was noted in the third sentence is correct, then this sample of CEOs would be biased toward that nebulous psychopath category. So the paper would be saying a sample with some categorical psychopaths has a lot in common with another sample consisting entirely of categorical psychopaths. Therefore, psychopathy is not categorical. Maybe, but this is a really poor way to show that. But as it stands, we are led to simply be impressed that the CEOs of the UK companies have trait profiles with, quote, significant elements of personality disorder traits. Compared to what? They don't say. Despite the conclusion of similarity, or continuity overall, the analyses can be read as a profile of key differences between some unsuccessful, i.e. detected criminal, and successful senior business leaders. My interpretation is that the analyses were actually done with this question in mind. What differences distinguish successful from non-successful people? Note that this is speculation, but this commentary on page 25 by the authors make me think that my speculation is correct. Zooming in, we have the senior manager group is more likely to demonstrate the traits associated with histrionic personality disorder and equally likely to demonstrate traits associated with narcissistic and compulsive personality disorders. At a descriptive level, this translates to superficial charm, insincerity, egocentricity, manipulativeness. This is the histrionic group. Grandiosity, lack of empathy, exploitativeness, independence. This is a narcissistic group. Perfectionism, excessive devotion to work, rigidity, stubbornness, and dictatorial tendencies, which are all compulsive. Conversely, the senior business manager group is less likely, this is what's attributable to success on the negative end, to demonstrate physical aggression, irresponsibility with work and finances, lack of remorse, this is the antisocial group, impulsivity, suicidal gestures, affective instability, that's the borderline group, mistrust, the paranoid group, and hostile defiance, alternated with contrition, which is the passive-aggressive group. In the speculative world, where these differences are what the research was actually interested in, we might ask why similarity was chosen as the important conclusion. In the abstract, the conclusion was about similarity, whereas there's a whole bunch of tests here for difference, and that page 25 commentary was about those differences. So the paper probably led with similarity because there are countless differences between the two groups being tested. The Broadmoor group is 14 years older on average, and only 5% of them are married and together, while 51% of the much younger business leaders are married and together. Any claiming that the observed differences are meaningful poses a problem of confounds and extraneous variables. Why should we believe the author's explanation? Maybe the histrionic traits do make you more successful. Maybe the antisocial traits do make you less successful. Maybe having the help of a female makes this average difference obtained. Maybe the only difference is age, so that in 14 years, the business leaders will actually end up in Broadmoor and divorced. Maybe the business leaders who participated in the study, filling out personality questionnaires, are the histrionic and narcissistic ones, or are not the antisocial and paranoid ones, and any differences or similarities are just a function of the very non-random and idiosyncratic sample the authors were lucky to get, the unique participators. Put another way, if you specifically care about how similar the average 36-year-old CEO who has enough time and motivation to complete psychological surveys is to the average 50-year-old psychopathic Broadmoor Hospital inmate in terms of trait scales based on personality disorders, then this is the study for you. But if that were the case, I doubt your conclusion would be one of similarity. But Professor, you say, I am charitable and wise enough to know that this imperfect study can inform me without being perfect. I just want to learn, as its title implies, whether to expect to find disordered personalities at my work. Okay, well, let's look at two interpretations of the title, Disordered Personalities at Work. First, one interpretation that the study informs us of what to expect at work. The article provides no cutoffs for disorder and no indication of how many senior business leaders met any cutoffs. It argues against those types of determinations and further makes no formal comparison to norms for any relative risk indication. No baselines, no relative risk metric, no information regarding what to expect at work. The other interpretation of this title is that the study shows how disordered personality of a given type leads one to either be a psychiatric prison inmate or a successful CEO, i.e. how disordered personalities work, or how disordered personality functions to get you places in life. For example, being histrionic and narcissistic makes you successful, and being antisocial and borderline prevents this success. The abundance of confounds make that interpretation of this data unwarranted. Unwarranted enough that this actual analysis is buried halfway through the paper. Okay, fine, Professor, but at least we learned something. We learned that narcissism is as common in Broadmoor Psychiatric as it is in CEOs. Nope. Right, we learned that narcissism is as common in Broadmoor Psychiatric as it is in our sample of CEOs willing to fill out and mail back a questionnaire about themselves. Not even. Not really. Only if we agree with the premise that categorical narcissism, i.e. cutoffs, should not be used, would we even care about this difference test. Maybe one group has a few pathologically high, i.e. categorical narcissists, and the other has none. Yet those few cases either influence the mean of the trait rating a lot, as would happen in the small sample, or not enough to be noticed, as would happen in the large sample. Such cases could have raised the mean in the smaller n equals 39 CEO group, making it look like the group has more trait narcissism than it does, or they could have been washed out in the larger n equals 317 psychiatric group, making it look like that group has less narcissism than it does, and maybe both of those things happened. I would argue that most people care about the extreme pathological categorical cases and not these trait averages. So most people would be either misinformed or completely uninformed by these analyses. Just like it did not give us a base rate or relative risk, it is not giving us anything other than mean trait differences, and hence is not informing us of the commonality nor even the relative commonality of narcissism. If the researchers had selected cutoffs from the relevant literature, then comparisons of the proportions of each sample that meet these cutoffs could be made. My rather cynical supposition is that this was likely tried, and they did not get the similarities that would make for publishable results. The headline, "Study Shows As Many Criminals as CEOs Are Narcissists," comes to mind, which is actually roughly how Andy Field represented this study. Whether 39 senior business managers had personality disorders was not actually assessed. We do not even know whether any individuals from any of the groups had personality disorders. If someone in the psychiatric group did, then they are just one data point in a distribution full of others who do not. The one person with a disordered level or combination of borderline traits is lumped in with the 316 who do not. He is literally the title character, borderline personality disordered individuals. He's literally the title character in the show, and yet we can't even see him in it. We don't even know if he's there. Just think of all the information their researchers have that lumping the 317 Broadmoor patients together conceals. An imperfect analogy that might help you view this data and its analyses the way I do. Imagine some people are assessing cancer risk in CEOs and compare trait measures of the CEO's risk to those of people in hospital in general, some of which may have cancer, but most of which would not. We're told either that similarities to the hospital sample indicates that they are at risk of cancer, so cancer at work, or that they differ on some sub-factor items in meaningful ways, which risk factors work to determine status. Such a study, with its terrible design, would surely not be seen as a contribution to science and used in statistics textbooks, right? The analogy could be improved by saying the CEO cancer risk scores were only compared to difficult hospital patients, since the comparison was to Broadmoor psychopaths. But I don't think that this waters down the critique here at all. But anyway, this is why I say rude things like I don't care about most psychological research, because reading most of it makes me think that the researchers are either foolish, dishonest, or so inside their own narrow world as to think that their random loose association mutterings matter. Usually I land on dishonest because being foolish precludes the skill of sophistry required to get nonsense or misrepresentations published. But maybe it's just me and I have all of the personality disorders, because this is supposed to be about running t-tests and I'm using it to tell you that epistemology is dead. Let's get back to R. First, let's grab our file. I've got it. I'm going to put it in a folder that I've created for this purpose. Here's what it looks like, in case you're curious. Just like last time, it's a tab delimited file. Now let's get started. First, I've got to set the working directory. Next, I'm going to create my object from the file. So I'll tell it to read the comma delimited file. And let's see if it grabbed it. That would just show us the first line. Yep, there it is. Looks right. Now what I'm going to do would normally be a few lines of commands. So normally I would use curly braces and make a big one big function, but I'm going to do it line by line. I want to do things piecemeal here, one thing at a time, so we can track what we're doing. So we need to work backward from our end goal. We want our p-value, but I need to get our t-score in order to get that. To get our t-score, we need the mean differences. We have the means divided by their pooled variance. To get the pooled variance, or pooled variances, there will be several. We need standard deviations, which we have, and degrees of freedom. So we can work on that first. Degrees of freedom for independent t-tests are easy. Degrees of freedom object will just be sample size 1, sample size 2 minus 2. We have an object, degrees of freedom. Let's see what we created. There we go, degrees of freedom. Same for all of them. What R is doing is it's running through the attached data and making a vector with a value for each row. In this case, each comparison. Now, next, we need the pooled variance, which can be computed quite easily from the standard deviations, sample sizes, and degrees of freedom that we already have. Pooled variance object is going to be this equation. We have to square the standard deviations and multiply them by their respective sample sizes, minus 1, which are very different. The sample sizes are very different, and divide by the degrees of freedom. This will not be an exciting result, but let's take a look at the pooled variances for each comparison by typing in poolvar. Here we go. Moving up our list, we want to compute t-scores now. So we'll make a t object. T is equal to the mean difference divided by the square root of the pooled variance divided by the sample sizes. Here we go. So what is t? The interpretation of these depends on our sample size, our degrees of freedom. So the t-scores alone are not too enlightening. What we need is to know the proportion of the null distribution that falls to the left of the observed test statistic t. How likely we are to obtain these data, this observed difference, in the world where both samples come from the same population. That's our question. We have assumed the null, and we've combined the variances, so our estimate of this single null population spread, because we have two samples, but we're assuming they come from the same population, so we pool their variance to estimate the population variance to inform our estimate of the sampling distribution of means to see how much we can expect to be off. So this is informed by both samples. The t-score is identical to the z-score from the Jenny example here. We can look up how likely we are to get that score. In the case of Jenny, she was 3 standard deviations above average, meaning she was doing better than 99.865% of grade 5 readers. What a p-value here would do is tell us how likely we are to get Jenny's or a similarly improbable score. So is this our p-value? 1 minus the probability density to the left of the observed score? Not quite. Note that I said Jenny's or a similarly improbable score, and significance tests, unless otherwise specified, have 2 tails. So we could get a similarly improbable score in the other direction, and we need to account for that. So our 2-tailed p-value is twice this. This is our probability of obtaining an observation like Jenny's from the grade 5 distribution. This is our p-value. But enough about Jenny. She's not the point. This isn't a z-test. This is a t-test. We need the t-distribution, not the z-distribution, and this t-distribution is a family of distributions. We need to specify which one via degrees of freedom. Let's take one of our t-values and find the proportion of the null distribution that lies to its left. We'll need the degrees of freedom to say which member of the family it is, and to get our p-value for this, we subtract it from 1 and multiply by 2. So subtracts it from 1, this just tells us that there is an actual value there, because it rounds to 1. And there's our value. We need to multiply this by 2. Let's quickly run another one. But of course we don't have to do these one at a time. We can make an object containing all of our p-values. And we could organize all the results together a bit, pasting 3 different columns together. And maybe do a little better by including labels in our paste function. This is kind of nitpicky with the spacing and details here. Without this SEP, this separation specifier, R would add spaces. I use it here to say no spaces other than the ones I put in my quotes. So we've obtained the t-values, which lie behind the p-values that we see in table 2 of the original article. And we did it all the grunt way, without downloading any packages. We used R as a calculator and as a reference source, which knows the t-distributions and z-distribution. Let's up the power a little bit and run through an example from chapter 9. Set our working directory. I have the spider long data. Now let's make sure it's there. There it is. Okay, and I'm going to use it. So let's attach it exclusively. So first, it's good practice to eyeball your data somehow. This is what the 24 data points looks like. Very good. It looks like I have a bimodal distribution, or bimodal density distribution. So let's take a look, because this is a t-test data set and it's anxiety for seeing a picture versus seeing a real spider. So let's separate my plot by those two groups, picture versus real spider. Nice, there we go. And we see, well, I don't know, this table's too small. We'll see. Looks like we have 2 distinct groups, and that real spider has slightly more anxiety associated with it. So for assumption checking, so this is good practice to eyeball your data first, but for assumption checking, I'm going to be using Welch's, so we don't need variance checked, but we do need, because our sample is small, we need to check normality. So we will use the Shapiro-Wilk test, and we will make sure that we have a p-value greater than 0.05, which would indicate normality. And we do. There it is. Wonderful. We will use, Welch's test does not assume equal variance, so we don't need a Levine's test. There's no test for interval level data, and independence is not an issue. Independence is a design issue. Now we get our difference test ready. We created an object, which I call diff test, and let's run it. So this runs a Welch's t-test. We have a non-significant p-value. Also, the mean difference is 7. So it's not nothing, but I guess the small sample size might be what's preventing us from getting significance. Fair enough. Okay, so next we need effect size. Let's make a T object. R is an object-based language. Just keep making objects and you can put them together. And degrees of freedom. Okay, so we just made statistics and parameters, so we're going to take advantage of them. So now we have T, degrees of freedom, and R. And I want to print R. And I'm going to have it round R to 3 decimal places. And there we go. So far, we have all the same answers as in the field textbook. In order to report in APA, we need the standard error. Since the standard error is just the standard deviation over the root of n, let's take a look at what our data limits are here. And what I need is the standard deviation of the anxiety group that showed the picture. And I can do that pretty easily by just selecting standard deviation of the anxiety variable, just the first 12 cases. Okay, so there we go. And what I'm going to want is that value to get the standard error. I need that value, so standard deviation over the square root of that group's sample size, which is 12. And for the other group, I just take the rest of the cases. And good, so I want 2 square root over of 12, because that group has 12 as well. So I have all of the values, and now I can report. On average, participants experienced greater anxiety from real spiders. The mean of the real spider group is 47, and the standard error of the real spider group is 3.18. Then from the pictures of spiders picture group 40, and standard error of the picture group is 2.68. Yes, this difference was not significant. Degrees of freedom. Here, well, it's just degrees of freedom. And t-score. Good. P greater than 0.05. Now it did represent a medium-sized effect, which we have here. R. That's how it's done.